Welcome to Talk Tensors, where we take a deep dive into the latest machine learning research. Today, we're looking at a paper tackling something pretty fundamental. Getting AI, especially these big foundation models and recommender systems, aligned with what we as humans actually want.
Right, which is, harder than it sounds given how diverse people's preferences are.
Exactly. We build these incredible tools, but are they really doing what we collectively need or prefer? It's a huge question.
Yeah, and the main approach, RLHF reinforcement learning with human feedback, it's powerful, sure, but it has its limits.
Okay, so what are we diving into specifically?
We're looking at a paper called Adaptive Preference Aggregation. It points out that RLHF often kind of lumps all user feedback together, like it's coming from one person.
Ah, okay. Like trying to pick one movie for a whole group, someone's usually unhappy.
Precisely. And this paper, well, it suggests a different way.
Adaptive preference aggregation sounds promising. So for you listening, the core idea is moving past that one-size-fits-all approach.
That's it. They've actually looked into social choice theory for ideas.
Social choice theory, like voting systems and economics, that seems unexpected for AI.
A little, yeah. But the problems are similar. How does a group make a decision? How do you aggregate different preferences fairly? They specifically use this recent urn process idea.
An urn process, like drawing balls from an urn.
Kind of. It's an analogy for a dynamic process. Imagine balls representing options. You sample two, a user picks one, and the loser gets replaced by a copy of the winner. It adapts over time.
Okay. And how does that connect to AI preferences?
Well, they connect this process to finding something called the maximal lottery.
Maximal lottery. Okay, break that down. And what's this Condorcet thing you mentioned earlier?
Right. So Condorcet consistency, it comes from voting theory. A Condorcet winner is an option that would beat every other option in a one-on-one comparison. Like if option A beats B, and A beats C, and A beats D, AA is the Condorcet winner.
Makes sense. The undisputed champion.
Exactly. A system is Condorcet consistent if it always picks that winner when one exists. But sometimes there isn't one clear winner. You get cycles, like rock, paper, scissors.
Ah, A beats B, B beats C, but C beats A.
Right. That's where the maximal lottery comes in. It's not a single winner, but a probability distribution over the options. Think of it as the best compromise strategy. It's a lottery that, statistically, a majority would prefer. Exactly. They argue it can work for both. Suggesting items, guiding text generation. It's quite flexible.
Okay, so how does this become an actual algorithm, an adaptive preference aggregation algorithm, or APA?
Right, APA. It's presented as both a new goal, an optimization criterion, and the algorithm to achieve it.
And the goal is?
The goal is essentially to find a policy, a way of choosing an alternative for a given user that maximizes the probability that this chosen alternative is preferred by a majority of users over any other alternative the system could have chosen.
Whoa. Okay, so it's like playing defense, making sure your choice is robust against all other possibilities.
Kind of, yeah. They frame it as a max-min problem. You want to maximize your minimum win rate against any competitor. It's very much inspired by finding equilibrium strategies in games. Think about the chatbot arena, for instance. You want a model that does, well, not just on average, but against its strongest rivals.
Right. Not just guessing what one user might like, but finding something with broad appeal across everyone.
Precisely. But, figuring this out for every single user individually is, well, impossible. We don't know everyone's exact tastes.
So how do they handle that? User embeddings.
Exactly. They represent users with embeddings, those dense vectors, capturing user features or history. The challenge then becomes, pick a good option for someone, only knowing their embedding.
And here's where the urn process comes back in, right? For you trying to picture this.
Absolutely. And they make a critical point about modeling preferences. Even if my preference is deterministic, I like A over B, when you only see my embedding, which might represent many similar but not identical users, the preference data you observe can look stochastic, even non-transitive.
Like that rock, paper, scissors thing again,
Yeah.
because the group represented by the embedding has conflicting internal preferences.
Exactly. And that's a big problem for traditional methods. Think about Bayesian Personalized Ranking, BPR, and recommenders.
Yeah, BPR tries to learn a score for each item, right? Based on clicks or purchases.
Right. It assumes there's some underlying score. And users prefer items with higher scores. RLHF does something similar. It learns a reward function, which is basically a score.
So for you seeing the limits here, these scoring methods inherently assume things can be neatly ranked.
Pretty much. They assign a single number. They can't really represent A, B, C, A. Those cycles just don't fit into a simple ranked list. Figure 2 in the paper illustrates this well.
So if scoring methods struggle, how does APA, their algorithm, get around this? What's the mechanism for you looking for the innovation?
This is where the neural urn comes in. It's not literal balls. It's a neural network.
Okay, a neural network acting like an urn. How?
So the algorithm repeatedly does this. It samples 2 alternatives, weighted by their current representation in this neural urn. Then it gets a preference signal, which one does a sampled user or user embedding prefer. And then, crucially, it updates the neural urn. The representation of the losing alternative is adjusted, nudged slightly towards the winning one. It mimics the urn process where the losing ball is replaced by a copy of the winner.
So over many iterations, this neural urn learns the collective preference distribution, converging towards that maximal lottery for users represented by that embedding.
That's the idea, yeah. And they draw this really neat parallel to replicator dynamics from evolutionary game theory.
Replicator dynamics, like species competing.
Exactly. The alternatives are like species, user preferences like fitness, how likely they are to reproduce in the urn. The maximal lottery, in this view, is like the stable equilibrium strategy in a competitive game. It's another lens for you interested in those theoretical links.
Fascinating. But okay, practicalities. How does this neural urn scale? Real systems have tons of users, tons of options.
Right. They use a multi-layer perceptron, an MLP, as the neural urn. It takes a user embedding as input.
And outputs.
It outputs a representation of the urn state for that user embedding. Think of it like the counts or weights for each alternative in this conceptual urn. Equation 3 in the paper shows this.
And the updates.
The algorithm uses specific rules, equations 4 and 5, to update the network's weights based on the sampled preference. The goal is to make the neural urn's output better reflect the observed preference. They also add a small mutation rate, equation 6, like in the original urn model, to keep exploring.
So it's like one network learning to manage many different urn processes, one for each user embedding type.
That's a good way to think about it. Different embeddings lead to different learned urn states, reflecting different group preferences.
But does it always settle nicely?
Ah, interesting point. They observed that sometimes, especially with strong non-transitive preferences, the neural urn state for an embedding doesn't settle. It can oscillate. You can see this in their figure 3.
Oscillations. That sounds potentially unstable for you, the end user getting recommendations.
It could be. So they added a distillation step.
Distillation, like in model compression.
Similar idea. They train another, usually simpler network to predict the average output of the main oscillating neural urn over time. The goal is to smooth out those oscillations and get a stable prediction of the maximal lottery.
Clever. Okay, so theory and algorithms, did they test it?
They did. They set up simulations. Users and alternatives were points in a 2D space. Preferences were based on distance users prefer closer alternatives. They gridded the user space to represent embeddings.
And they compared APA to what?
They compared APA's output to the theoretical maximal lotteries calculated for each grid cell and also to the Borda winner.
Borda winner, why that?
They argue the Borda count method, which sums up rankings, is kind of analogous to what score-based RLHF implicitly optimizes for. Their evaluation metric was win rate, how often APA's choice beats a random competitor according to the majority preference in that grid cell.
In the results, what's the key finding for you assessing this approach?
Pretty encouraging, actually. Even before distillation, the raw neural urn achieved a win rate near 0.5 against the true maximal lotteries on their grid, essentially performing randomly against the optimal, which isn't bad given the complexity.
Okay, 0.5, like a coin flip against the ideal. What about after distillation?
After distillation, APA performed comparably to locally computed maximal lotteries on a coarser grid. Table 1 shows this. And importantly, it often outperformed the Borda baseline, suggesting it is capturing something beyond simple scoring.
So it seems this urn-inspired approach genuinely shows promise for handling those complex, maybe cyclical preferences that scoring methods miss, for you seeking better preference learning.
That's the takeaway, yeah. But they're rightly cautious. It's early days.
What are the caveats, limitations?
Several. They need more work on the theory. When exactly does this work, under what conditions? Sample complexity, computational cost are big questions for real-world use.
Makes sense. Anything else?
They also mentioned they haven't fully integrated ideas from collaborative filtering yet, leveraging user similarities. That's standard in recommenders. And there's this big open question about evaluation industry often uses engagement metrics, clicks, watch time. How does that square with maximizing this Condorcet style win rate? Are they compatible?
Yeah. The definition of better is tricky.
Exactly. Plus, they need to look deeper into generalization. How well does it predict for new users?
Yeah.
And the statistical properties of the lottery estimate itself need more analysis.
It really drives home how tough this alignment problem is. It's not just finding an answer, but navigating all these diverse, sometimes clashing human desires. Connecting it to social choice theory feels like a really fresh angle for our field.
Totally agree. For a long time, alignment research felt very focused on tweaking RLHF, refining reward models. This paper says, hey, maybe we need to look at the aggregation mechanism itself. Social choice theory has wrestled with these paradoxes for decades. There's a lot of wisdom there we could potentially leverage. It's a whole new direction for you and the ML research community to explore.
Okay, fascinating stuff. Let's shift gears slightly to our novel notions segment. Taking these core ideas, adaptive aggregation, neural urns, social choice links, where could this research go next? What's a potential future direction for you thinking about building on this?
Well, one thing they mentioned is fixed user embeddings. What if those embeddings weren't fixed?
You mean they could change over time?
Yeah, exactly. Imagine the APA system not only learning the preference distribution for an embedding, but also learning to refine the embedding itself as it gets more interaction data from that user.
So the system learns who the user is becoming in a sense, while also learning what people like them prefer.
Precisely. It could lead to much more dynamic, context-aware aggregation. If you're familiar with recommenders, it connects to dynamic user modeling, but adds this social choice aggregation layer on top. It can be really powerful.
That does sound powerful. What's another notion? Maybe something a bit further out.
Okay, here's a more ambitious one for you to chew on. Right now, APA selects or ranks existing alternatives.
Yeah.
What if it helped generate new ones?
Generate. Like an LLM writing a response.
Exactly. Instead of just picking the best response from a set the model already generated, could the APA mechanism somehow guide the generation process itself? Steer the model towards outputs that are more likely to represent a maximal lottery in the vast space of possible responses.
Whoa. How would that even work?
That's the tricky part. It's speculative. Maybe you could integrate APA principles into the decoding strategy, or use it to shape the training objective for the generator. It's a big leap from ranking fixed options to guiding continuous generation. Huge technical challenges, for sure.
Definitely sounds challenging, but the potential payoff. An AI that doesn't just pick the best existing option, but actively creates options designed for broad appeal.
That's the blue sky vision, yeah. Using social choice ideas, not just for selection, but for creation.
These are really cool ideas. It highlights how bringing in concepts from other fields like social choice can spark totally new avenues in machine learning for you, the researcher.
Absolutely. This paper feels like a great example of that.
Yeah.
It encourages us in ML to maybe rethink some core assumptions about alignment and preference aggregation, moving beyond just reward maximization.
Definitely. It's a complex space. If you want to get into the real details, the math, the specific algorithms, we strongly recommend checking out the full paper. We've put the link in the show notes for you.
Yeah, definitely worth a read.
And for everyone listening, here's something to mull over. Given how messy and diverse human preferences really are, what other ways beyond what we discussed today could we design AI systems that truly try to align with what a whole group, a collective, actually desires, rather than just optimizing a simple metric? It's a question that's going to be central to AI development going forward. Thanks for tuning in to Talk Tensors.